Well, thanks a lot. Can everyone hear me?
Yes.
Okay, good. So I really appreciate the opportunity to be able to give you a presentation here on my current thinking at OCI and plans we have for the future. I hear there's a lot of background noise. Okay. I think I'm hearing my own echo a bit, but I'll just power through it. So my background, as Jose Marie told you, is in astrophysics and relativity. And if you see the picture on the cover, the front of my presentation, it's on gravitational waves. That's the visualizations of gravitational waves. But boy, this is very difficult. I'm hearing my complete echo here. I'll see if I can get someone else to help us in the background here. But meanwhile, I'll just keep going. So we have this. It's much better, by the way. Thank you. We have this visualization of gravitational waves from black holes colliding, and I'm going to continually refer a little bit back to astrophysics, but more or less only on the kinds of lessons I've learned in the applications that drive the future development of cyber infrastructure. But in particular, I want to illustrate here on this cover that it's about high-performance networking. And so through astrophysics, I got dragged into many, many different application areas and into many different kinds of cyber infrastructure. And so today I want to tell you about what I've learned through those experiences and what I think that means for the national cyber infrastructure. And in particular, I hope it gives me an opportunity to hear from you what you think we should be doing. I've been spending a lot of time listening to the community. I have probably, I'm on my 4th notebook, almost finished with that one in terms of input from people. And we're turning this into some task forces and into some input that we're planning to get from the communities. And I hope that by the end of this presentation, you'll have some ideas about things you'd like to help contribute to. So let me start a little bit by explaining a little bit more about my background, but specifically in ways that help inform me about cyber infrastructure. So the first thing is I have these illustrations. By the way, these are illustrations of work. I've been very fortunate to work with some very great people in scientific visualization who've helped us get a lot of magazine covers, but everyone has a little story behind it. So I'll start off by saying the first one here is actually a gravity textbook on the theory of general relativity. And when I was a graduate student, I had the very wrong idea that the hard part was just learning the basic science theory, in this case general relativity, and then when you were ready, all you needed to do was code up the equations on a computer and then run a simulation, and then you'd get your physics out. And so I've learned over the last 20 or 25 years that developing working code is about as hard, or in fact many cases it's harder than actually doing the theory. So there's an entire discipline that's been built up that I'm going to focus on a lot in this talk of computational science. And that's something that is just as demanding as any of the theoretical aspects of things that the scientists work on, and it needs to be done hand in hand with the science activities. And so that's lesson number 1 that I learned. Lesson number 2, by the way, that's a visualization of 2 black holes colliding, the first time that was able to be simulated on in a 3-dimensional form on a supercomputer. But that particular visualization required rather a large team. So I come from this area of general relativity that used to be, in the old days, maybe 1 professor and a grad student. That was the extent of the team. Now we have very large teams that involve literally dozens of scientists. We're kind of getting to the stage that the high-energy physics community has been at for quite a while now. And it's very common to see these kind of things in virtually every area of science and engineering. So that's another one of my themes that I'll be coming to. But in this particular case, we had people from the computer science community, the mathematics community, the general relativity community, the astronomy community, working together, and virtually every one of those groups was involved in creating a code that could run on a 512 processor machine where we could then visualize the results, and we had to worry about parallel algorithms and many things that the physicists themselves were not really schooled in. And so the lesson there is that grand challenge teams are critical to success for solving complex problems. Then I moved to Germany in 1996. And I was still trying to use supercomputers back in the United States, particularly at the University of Illinois, where I had come from. And I learned that international cooperation and networking are extraordinarily important. And so, for example, we had such limited bandwidth that we weren't even able to log into the machines at NCSA from Germany without getting a timeout before we could type our passwords in. So some of you probably remember those days. The network bandwidth was so limited that it was almost impossible to do our work. Now, bandwidth has increased a lot, but the size of the data that we have to deal with has also increased dramatically. And so we're still at a stage where it is almost impossible for us to work with the remote instruments, supercomputers, data archives, and so on that we have, because we don't have sufficient bandwidth, and we don't have the right kind of end-to-end connectivity from the lab or the desktop to whatever it is. That's going to be increasingly important, not only because of the data, but because of the collaborations that will be needed for carrying out the work that we want to do in solving complex problems. Well, I began to build out larger collaborations. I had a couple of collaborations across Europe that involved something like 10 institutions, in this case trying to solve the collision of two black holes, but in other cases we branched out into other areas, and so we had to bring in different disciplines. But that drives a lot of activity in software engineering, which most scientists have absolutely no training in whatsoever. And for example, version controlling, software abstractions, the ability to create interfaces that allow people to collaborate, those are extraordinarily important and require not only computer scientists and information scientists to be working with these teams, but also basic research into what are the proper abstractions to allow the collaboration between different groups. Now, in many cases, we're talking about collaboration between different groups, not in a tightly knit team, but in virtual communities or virtual organizations these days, where the groups may not ever even meet each other, but they critically need each other's work. And so there needs to be a lot of discussion on how one shares data, what are the right intellectual property issues there, how do we encourage collaboration, knowing that also that there's competition between these communities, and how do we enable, through software engineering, the ability for the groups to actually work together effectively. So these are all research topics that are being addressed to some degree, but we need much more effort on this. Well, I began to get involved not only in the basic science of these activities, but also the distributed environments that people work in. And so we have geographically and not just temporally distributed teams. Another important thing I learned is not just the fact that you live in a different place, but you live in a different time zone. And so that leads to very different social interactions and ways of working that, for example, you just don't work at the same time between Illinois and Potsdam in Germany, and therefore there are often delays in timing, and the communication can become more difficult. The collaborative environment becomes much more complex, so a lot of social issues become very important. Also, the issues of that grid computing has been trying to address for many years became important. So I became very involved in that community and began to see how important that was for gluing together the kinds of collaborations that were needed. Well, as you'll see throughout the talk, I illustrate this a lot with illustrations and visualizations from my work. As people develop larger and larger data sets, of course, being able to understand what the data are telling you becomes more and more challenging. And so visualization, remote collaboration, those are all very important. The size of the data sets is getting to be absolutely unbelievable. I'm not going to talk much about high-performance computing in this talk, but just as an example, there's a facility going into place at the University of Illinois called Blue Waters that's supported by the National Science Foundation and specifically by my office. That will be operational in about 3 years. I've calculated from my own area of science, we would run a simulation on that machine that would easily generate 5 petabytes of data, and that's assuming we downsample tremendously. Then we have to think about how our team actually gets to that data, remotely visualizes it, distributes the data, how we really figure out what it is telling us about the science. So those are tremendous problems, and they're going to get much, much worse and very rapidly. So this leads me to the next thing, the need for optical networks as one of the technical issues that we have to focus on. How do we move the data around? And how do we bring it to the home institution or to the individual scientist? But another thing, as Jose Marie told you, I was involved in setting up an optical network initiative in the state of Louisiana. And quite frankly, the most important impact of that optical network initiative had very little to do with the data, but it had to do with the sociological change of the state, because the universities were suddenly connected at high speed, and then they began to realize that that provided new opportunities for them to work together, and there's been a culture change there that's still ongoing, but where you have groups of universities and research groups within the universities working together in ways they never imagined just a few years ago, and that is leading to a lot of new funding opportunities and new research opportunities for the state, and I've seen this in regional optical networks across the country and across the world, and so that's a very important point here. It's not just about the data, it's very much about the kinds of collaborations that are enabled by this. Well, living in Louisiana for the last 5 years, I've learned a lot about other kinds of science beyond astrophysics, in particular coastal modeling, hurricanes, storm surge calculations, and so on. And this is a visualization of some storm surge calculations that my group became involved in. And so one very important point there is that many disciplines can use the same components. And so it's a bit of an art to figure out at what level you need to differentiate, but it's clear that there's an awful lot of reproduction of the wheel by many different communities, and we need to work very hard to find ways to come up with a reuse strategy so that people can take advantage of other people's work more easily. And so in this case in particular, software environments we had developed for astrophysics could be used with virtually no modification to support the kind of coupled models that you find in storm surge, hurricane, and atmospheric models as well. So the last one, now that I've come to NSF, that's actually the cover of the 2006 budget request to Congress with a black hole collision on the cover. I was very proud of that. But now I begin to realize, from feeling a bit green, how much all of this actually costs now that I have responsibility for it from the Office of Cyberinfrastructure. So this is a very, very expensive business, and we need to have, obviously, as much funding as we can afford in these areas. So that's the kind of the introduction to what I'm going to tell you. Now I'd like to tell you about the outline of my presentation, because there are some messages I want to make sure actually come through. The first one is going to be that complex problem solving is really what drives everything we should be doing in scientific cyber infrastructure investments. So as you'll see, I'll give you a few examples of this. This will require multidisciplinary collaborative teams, hardware and social networks, and virtual organizations, and we should be doing this in a way that's very well informed by the science activities. And so, as you'll see, that will be one of my very strong themes going forward in the future, trying to make sure the design of the programs we have is well connected or well motivated by the science activities. Increasingly, data and software are the big problems, not the compute cycles themselves. We've done a very good job in building out a lot of high-performance computing facilities, distributed, connected, and so on. We have a lot more to do in the areas of data and software, and those will be the areas where there will be increasingly larger investments as we go forward. There needs to be an architecture to figure out how to pull all of this together. So we want a coherent, integrated, high-performance cyber infrastructure that really reaches all the way into the campuses. So if we develop a grand national cyber infrastructure, but all of the PIs that we fund are on campuses and they can't access it, it doesn't do them that much good. So that's another emphasis that we'll be focusing on more in the future. How do we actually bring this to the campuses, and how do we integrate the campuses as part of the national cyber infrastructure? And so you'll hear more about that as I go forward in my talk. The last point, and I think the most important one, is that cyber infrastructure is about people and their ability to use it. And so the Office of Cyber Infrastructure has up to now focused more on the things, the hardware, and less on the use. Not that was the wrong thing, that was the right first step, but the next step is figuring out how to build out those activities. And so OCI is increasingly going to be about people, and in particular, developing computational science as a discipline. And I mean that in a very broad sense. To some people that means high-performance computing. To me it means how do you take advantage of the comprehensive investments in cyber infrastructure, including computers, networks, data, sensors, observation systems, and all of that integrated, and then to build the science on top of that. And so how do we support that in academia and in the agencies. For example, I'm trying to develop a theme for the Office of Cyber Infrastructure, OCI, to become more of a home for those kinds of activities. And I'd like to work with academia to figure out how to make it better supported within the university structures. Typically, computational science is done a little bit in some departments and a little bit in some schools, but it's often at the fringes, and it should be more in the central location of the university structures, and that means there needs to be rethinking about how universities are actually structured, and so we'll get into this, but I'd really appreciate your comments since you're probably at the forefront of thinking all of this through. Okay, so let me turn to a couple of science activities just to show you the way I'm thinking of this as how it informs the development of cyber infrastructure. So in my background, I think about not just black holes. That was one of the, by the way, the Grand Challenge projects from the early 90s when there was a Grand Challenge program at NSF that actually was in some ways aimed at making sure that there were parallel applications that could run on a large computer. And in fact, we had 8 universities cooperating to try to develop a program to solve the problem of 2 black holes colliding, but that was basically just physicists and mathematicians and computer scientists. Now we're talking about much more complex problems, and in this case it would be gamma ray bursts, where you also have to bring in people who know about radiation transport, equations of state, nuclear physics, neutrinos. They may sound, if you're not working in that area, like they're all in the same area of astrophysics, but these are entire communities that basically don't talk to each other almost at all. Magnetic fields, the astronomy of these, and then the gravitational fields, the general relativity. So you need to have very, very different communities brought together to solve these problems. And then they go beyond theory. So I have a picture there of LIGO, the Laser Interferometric Gravitational Wave Observatory, or LIGO, which is in some ways a remote instrument. So think of that as just the instrument now that people doing general relativity have. There are 2 very large instruments, one in Washington State, one in Louisiana, and several others being built around the world, so that this formerly very theoretical science is rapidly becoming a data-driven science where petabytes of data will be generated, and they have to be brought together to globally distributed communities of collaborators on the theoretical and the experimental side trying to do science here. This drives incredible activities in cyber infrastructure development that we have to be thinking about, in particular in my office. The next thing is the Large Hadron Collider. So there's a picture of this facility, which is just outside of Geneva, Switzerland. It actually, this particular instrument, if you're not very familiar with it, actually straddles 2 countries, France and Switzerland. It is miles across, or kilometers across in European units. It's supporting 10 to 15,000 scientists in about 3 dozen countries, generating many petabytes, dozens of petabytes of data, and it's really a planetary lab for scientific discovery. That is a collaboration that really only involves something like 6 different experiments with tens of thousands of scientists. So this is a collaboration at the extreme level, and it's driving technology and algorithm development in a massive way. So that data is not being centrally stored and then remotely accessed. It's being globally distributed in a hierarchy of data analysis sites around the world, and being brought right into the labs. And so this, of course, creates a tremendous need for networking and many other cyber infrastructure investments. So let me just move to the next slide. So when I come back to the issue of storm surge modeling. So I talked about some individual communities and how even within those communities there are many different communities, but this is where I see a lot of these activities going, and I think this coastal modeling program really illustrates this. So this is the hurricane tracks for Katrina, and I was living in Louisiana at the time, so I really experienced this firsthand. Early on, as you can see in the illustration there, those are the black dots represent the actual locations of the hurricanes, the hurricane at various times. The different colored lines coming out of it represent the storm tracks of different models. So these are different models that the community has developed, and around 3 days out, right around here, the models more or less converged on New Orleans, but early on they were quite different, and so we really had no idea where that hurricane was going to go. or how it would intensify, or what the storm surge would be like that comes from that. And by the way, these are run by different kinds of models. So for example, the images you see there are just of the atmospheric models, but the thing that really matters to the people living in the coastlines, of course, the winds are important, but the storm surge is the killer. And that is what led to the deaths of nearly 3,000 people from this particular hurricane. So you have then models of the storm surge, which basically say how do the hydrodynamics develop as a function of the forcing functions of the winds that are blowing the water around. And so depending on which one of those tracks turns out to be correct, you might have one storm surge model or another one that has to be invoked. So there's a dynamic data aspect to it. We'd also like to be able to stream in data from observation systems in the Gulf of Mexico and from satellites and reinitialize all of those models and automatically compare with the instantaneous or the short-term projections of those models to figure out which one is doing the best job, so we can figure out sooner which of these models is reliable and therefore which storm tracks to believe in. Now, as you go beyond the issue of just the atmosphere and the water, then there are issues and the storm surge, there are issues of the waves. So there are different models that are used to forecast the waves and how they would develop on top of the storm surge. So now you've got a highly complex problem that involves many different communities with different kinds of codes that need to be dynamically invoked with data streaming and then instantaneous comparison with data coming from these different systems. And then you'd like to go even further and look at how the levees will respond because of the stresses that will be developing because of the water that will build up, where supply should be put, how traffic patterns might develop because of the storm surges and the hurricanes coming, where there would be jams, where they should put supplies, how the microwave towers are going to respond, et cetera. So you bring in virtually every community in this emergency response area that you could imagine, and it's one of the examples, and if you look in virtually every other area of science, you find these kind of things. So you cannot have any grand challenge team looking at this. You're talking about bringing together communities that can work together, and they may never know each other, but the results may have to be instantaneously connected together through a dynamic process. So, summarizing this, I wanted to build up to this idea of these grand challenge communities and the fact that collaborations are one of the great challenges of the 21st century that we're facing in science. And the other aspect of it is that's becoming increasingly data-driven. And so every field of science, from my own area in general relativity, where the kind of data we used to output would be several pages of equations or maybe 100 pages of equations if you're unlucky, now we're talking about petabytes of data, and you see this everywhere, from the very pure sciences like general relativity, the more formally the comprehensive sciences in astrophysics, geosciences, biology, and so on, and then branching out into the social, behavioral, economic sciences as well. They're all needed often to solve single complex problems. So in this sort of set of illustrations, we have in the beginning we have science, and at the end of it we have what's called the end of science. A few months ago, around the time I decided to join the National Science Foundation, Wired ran a very provocative cover story called The End of Science. So I always thought that was kind of amusing to come here when science was supposedly over with, but basically science as we know it may be over in the sense that it's changing dramatically. So this drives new methodologies, new approaches, and new paradigms. In particular, data-intensive computing is now in some quarters now called the fourth paradigm of science. And so things are really very dramatically changing. By the way, the Pampers illustration there actually is serious. I had a very interesting discussion with some groups at the Council on Competitiveness once. So Procter & Gamble in particular was there, and some of you may know Tom Lang, and he gave a very impassioned speech on what he called fluid flow in porous media, where they're looking at doing simulations, of course, of fluids in diapers, and how they're orders of magnitude away from being able to have enough computing power to do this at the level that they'd like to. And the most interesting discussion I had there was between him, a group from Morton Thiokol, and me as an astrophysicist. And you think what we would have to talk about, but we talked about multi-scale simulations and the fact that we basically all had the same software environments that we needed, but we at the moment have no way to share knowledge about how to do that, and so we need to find ways to do that in the future. So, with that as a prelude, I'd like to get into a little bit about the vision that NSF has developed to support all of this. And I want to walk you through the areas where we're making investments and where we hope to make investments in the future. And I hope to see many of you writing proposals for these programs that we hope to be developing in addition to the ones we already have. But about 5-6 years ago, I guess, Dan Atkins, as you heard, the person who initiated or inaugurated this office of cyber infrastructure, led a task force that came up with a blue ribbon task force that came up with this white paper called Revolutionizing Science and Engineering Through Cyber Infrastructure that made a number of really sweeping recommendations that really did lead to the founding of this office, and so these reports can have major impact. Of course, Dan of course had to come in and run the office for a couple of years as a result, but I know he enjoyed that and had tremendous impact, and that led to this document called Cyber Infrastructure Vision for 21st Century Discovery, which if you don't know it, I assume many of you do, but I'd encourage you to read it and reread it. I often come back and look at it again. That is really the high-level blueprint for what this office will be doing in the future. And it has in particular four areas that are to be focused on, and I think they're right on target, and that is the high-level roadmap for us. But as you'll hear, we're going to have lower-level roadmaps in the form of task forces to help us come up with more specific plans going forward. But the primary areas here are virtual organizations for distributed communities, high-performance computing, data and visualization and interaction, and this is built on top of perhaps the most important long-term need that we have is learning and workforce development. How do we train people to live in this really disruptively changing world of cyber infrastructure? So what's being done to address this? Let me go through and kind of walk you through some of the programs we have. So I'll start off by saying high-end computing. High-end computing is much more than high-performance computing. It is grids, it's distributed computing, it's the collective power of computers in campuses in things like Einstein at Home, some of you might have heard of, or the SETI at Home. There are many, many activities, and so although most of our office has been focused up to now on the activities in high-end computing at the level of HPC centers, there's much more to it. And so the areas where we will be focusing much more activity in the future, I've now highlighted in red. Modeling and simulation, from data collections, going beyond traditional HPC, especially developing software and tools. We need to have much, much more activity in those areas. The computers themselves are becoming increasingly difficult to use, and so we need to develop much more sophisticated toolkits. And as you'll see in a minute, we need to have toolkits that go way beyond high-performance computing, but toolkits that enable people to take advantage of the extraordinary complexities of the comprehensive cyber infrastructure environments that we're deploying. Developing the ability for sharing of computing resources, especially those that are deployed and supported at the campus level. So for example, with MRI proposals, the major research instrumentation, we will increasingly be asking people to show how those contribute to the national cyber infrastructure, or how they might catalyze activities on their campuses that will train people to take advantage of cyber infrastructure and so on. The kind of investments that have been made in the last few years are dramatic in high-end computing. So this just shows in a bar chart here the growth of computing cycles from just a year and a half ago to the present day to what will be deployed in the next year. And you can see we're up by a factor of well over 10 in terms of the investments in computing. So we have a lot of computing capacity. And as I mentioned, the machine called Blue Waters that's going into operation at the University of Illinois in the year 2011 will have another factor of let's say 5 to 10 over this level of computing capacity. So at the high end, there will be tremendous amount of computing cycles available, but there's a lot more to be doing than that. So I'll focus more on that, on the other things we should be doing. So the second area, not listed in order of importance, just in the order that I have them on my slides here, are data analysis and visualization. And so this is just quoting, by the way, from our strategic plan from that cyber infrastructure vision document. from the executive summary. And basically it says we better be doing a lot more in data. And if you look on the cover of virtually any science or computer magazine, increasingly it's about big data, not just the huge data that are generated by a few large experiments, but what some people call the long tail of data, huge amounts of data that are collected by smaller groups across many, many, many institutions. And how do we bring that together and make it possible for people to collect that data, mine it, and then in particular to bring different communities together to solve complex problems again? I'll get to this in just a minute. So these are the areas that we plan to be focusing a lot more activity on. And I think data is probably the biggest challenge facing all of science right now, to be honest. In terms of technical challenges, it's the biggest one. I would say high-end computing, there are many unsolved problems there, but we basically do know how to build a parallel computer, and we basically do know how to write software environments that take advantage of parallel computers at some levels. Of course, there are many unsolved problems, but I'm saying compared to data, where we don't even understand what the basic methodologies are for mining the data, collecting it, what the sociologies will be about how people will come together and so on, that's a bigger unsolved problem to me right now. So as a simulation scientist, I want to be able to visualize my results or compare with experiment, but that's just my own personal view. These are questions that I would have and many in my own community would be having, and data is increasingly becoming the thing that they worry about now too, not just the simulation side. So now there have been many reports that have been informing us about data. And so I just list a few of them here. You can get them, if you haven't read them, you can get them from our websites or from the slides here. But I'll say even at the level of storing data alone, we don't know how to store all the data that are available because we can't. In fact, more data are being generated than we have the physical capacity to store. And so there's this report by the Storage Networking Industry Association saying that there's a pending crisis just in the archiving of data alone. We don't know how to store data. By the way, those of you who have been doing any kind of data on computer for more than, let's say, 5 or 6 years, have probably already run into the problem where you have something that you can't read any longer. So although we can still read the Gutenberg Bible after over half a millennium, we cannot read, for example, the diskette that has my own PhD thesis on it. just can't read it anymore. Nobody thought about preserving that, so that's gone. I have a hard copy. That's kind of going back to the Gutenberg Bible model, but we have to figure out how we're going to be saving and curating data. We also think about what's the sustainability model for this, what's the business model for this in the future. We've done a very poor job of thinking through how we preserve data, how we're going to afford it, and this goes in other areas as well. For example, software investments. We tend to fund people to write code at the grad student level, and beyond that, it just dies and then somebody else writes a new code. We have to figure out better ways to sustain these kinds of activities, and we're struggling with that. We don't really have the right answers yet. All right, so where there's a crisis, there's an opportunity, and I think we do have an opportunity in the U.S. to take a leadership role here, making it a national priority, and I certainly intend to be doing that. The kind of things we are doing already, and I think they're a drop in the bucket compared to what we'd like to do in the future, the so-called Datanet program. It's a $100 million program that's run out of SAIS and OCI, primarily out of OCI, SAIS being the Computer and Information Sciences Directorate. We have very good partnerships with the different directorates, by the way, and Jeanette and I talk a lot about, Jeanette Wing, the AD for SAIS, talk a lot about the important and phenomenal growth in data and how we're going to be developing new programs around this. And your input is highly desired in this. But in Datanet in particular, we're planning to build out, much like the national supercomputing centers were built out about 20 years ago. There were initially 5 centers at a time when people weren't really sure how the simulation science would develop. Well, that's kind of where we are with Datanet in the data area. So Datanet is in some ways analogous to the earlier foray into the supercomputing centers, where we will be making awards at the level of $20 million each, roughly 5 of them, that should be catalyzing communities to work together to bring data from different communities together to look at problems, for example, climate change, ecology, biosciences. Those are areas where there are incredible needs in data. When we talk to those people in those directorates, those are the things they're mostly concerned with. So there have just been 2 awards made, and this year there's a set of proposals that are in and are being evaluated, and we hope to make 2 or 3 more awards in the next year or so. The next area, the last area, but the one that's closest to my heart in terms of the scientific content, is the virtual organizations for distributed communities. How do you bring communities together to solve large-scale problems or even small-scale problems that may need to be more connected than they typically are? So many small-scale problems often need to be connected in various ways to kind of to grow the bigger picture. I have a picture there of a collaboration that I was leading in Europe. We had funding from the European Commission to do problems in astrophysics, and you can see that collaboration involved about 70 people or so, and we had several key areas of science problems, and they were all in various ways connected to each other, and that's very much what virtual organizations are all about, finding ways to bring communities together to solve complex problems. So we will be making much more investments in these areas as we go forward. And so I'll be more specific about this when I get to the task forces towards the end of my talk, but that's all I want to say about it for right now, except for the existing programs we have in place right now. So we do have a thing called VOS, Virtual Organizations as Social Systems. So that is one where a program that's underway that we expect to be continuing next year, where we're having people study virtual organizations to understand what are the issues they face, what makes them effective, this is a research program on studying and understanding virtual organizations, and I hope very much to take the output of those studies as input into the next round of grand challenges or complex problem-solving programs that we have here at NSF a couple years down the road. There's another thing called CDI, a program that I'm sure you're all familiar with, that's run by SAIS and many other directorates here at NSF, and so there is a lot of activity there. That program is likely to be growing in time, and so you should be seeing more about that as time goes by. And then we have a number of virtual organizations that are associated specifically, in some cases, with the TeraGrid and other activities we have in terms of the high-performance computing environment, where, for example, they have science gateways, where they have community codes and community data collections that are brought together through portals that different communities from across the country can collaborate through. Well, let me move on a little bit. I think I got a little bit out of phase here. I meant that was the third of the 4 areas. The last one, and probably the most important in terms of long-term development, is learning and workforce development. How on earth do we train people to live in this new world when it's moving so fast? And it goes against the grain of many of the organizational structures that we find in universities. And so, in particular, I would like to see what we could do to break down the barriers to using these tools and to how to educate people in a multidisciplinary, collaborative way that really exploits and explores cyber infrastructure as a fundamental part of our of the background on which we do science. So this is a student saying, I need to learn more about this. So we did have a task force last year that led to a very, very nice document called Cyber Learning, Fostering Learning in the Networked World. And this is available on our website. I also have a couple hundred copies of which I would be handing out there if I were there. It's a very nice report, and we're now taking this report as input to a new generation of programs that we're working particularly with the Education Directorate here, thinking about, for example, how to bring many of the research activities of NSF through now the advances in high-end networking, how to bring those directly into the classrooms. And it's not just about technology adoption, it's thinking deeply about what are the new modalities for learning that should be developed in order to take advantage of this, not just the old, let's build better laboratories in our classrooms, but let's think about how to take advantage of LIGO, the TeraGrid, space telescope, radio telescopes, etc., to bring these directly into the labs, to build learning modules around them, and to link together students in classrooms from around the country and around the world. Okay, so that's an overview of the different areas. I'd like to get in a little bit into the activities, what is the national cyber infrastructure blueprint? And so this is going to be a very messy diagram, but my main message here is that it's very comprehensive, and there's much more to it than the Terra Grid. So you might have thought that the Terra Grid is what I mean by the CI blueprint, but watch what I'm saying here. The Terra Grid is 11 service providers that are knitted together by services and high-end networking. On top of that, we're making large investments in supercomputers, the so-called Track 2 program. That's continuing this year. We have a number of sub-programs in Track 2. These are typically $20 or $30 million programs. In the past, they've led to one single award each. This year, there will probably be 4 or potentially more awards for smaller facilities. The Track 1 facility is the very large supercomputer Illinois that I've mentioned several times. An expansion of the Terra Grid program, or an extension, I should say, Terra Grid Phase 3, sometimes called Extreme Digital, or XD, has remote visualization components in a new round of services. That is currently under review right now, but it is let's say, scheduled to be funded at the level of around $30 million a year, similar to the current Terra Grid. But that's under review, and so it may be a while before the dust settles on that. There's another kind of computing that I would like to see embraced more strongly by our office and to find how to integrate this. This is more of the distributed computing model that's pioneered in part by the Open Science Grid in the US and by similar operations in Europe in particular. So OSG stands for Open Science Grid, and LC stands for loosely coupled. So these are computing environments that typically reside on university campuses. Collectively, they make an awesome national cyber infrastructure, and so we're looking at ways to integrate that more tightly into the entire national cyber infrastructure blueprint. So that's where the campuses come in. The campuses, by the way, I feel are one of the highly overlooked aspects of the national cyber infrastructure, and so we have an entire task force called Campus Bridging that we're trying to launch here that will be focused on how do we revolutionize the environments on campuses and make it possible for the individual investigators and students to be more tightly integrated into national cyber infrastructure. So I'll have a few slides on that as we go forward. So this is bringing the people in. Now, networks, of course, are what link everybody together. We, in some ways, do not even have a national networking program at the level of connecting the individual sites. That's really been provided, thankfully, by organizations like Internet 2 and the National Lambda Rail, and so we are working on ways to partner more deeply with them. Campus networks are extraordinarily important here. The last mile problem to your individual labs, if we develop all of this and you're generating 25 petabytes of data somewhere and you have a 100 megabit connection to your desktop, you're basically dead. You can't do much with it, and so that's another aspect that we need to be figuring out what to do with. So keep going, because we're just getting warmed up. Datanet will be integrated into these things as we build out 5 or more Datanet nodes. Going beyond in the high-end, very high-end computing area, of course, we're talking about exascale computing. Wow, how can any agency do that alone? We will probably be working together, and we are already working together with agencies like DOE to think through what comes beyond the petascale. But I won't talk much more about that. I think where the real activities are in terms of the things that need to have much more attention: software, algorithms, other computing modalities, clouds, and so on. Remote instruments. We need to think about, for example, how we integrate in the remote instruments. And you may have, on top of that, of course, applications that take advantage of not just one of these, but as I tried to illustrate with the coastal modeling example, they may bring in everything in one single application. They have algorithms, they have remote instruments, they have satellites, observation systems, grids, high-end computing, connected communities, virtual organizations. So that brings in this idea that you have multiple application areas brought together by virtual organizations. And then you have a poor student here saying, I potentially need all of this to start to solve my problem. And that's the thing I'm trying to think about much more deeply. How do we integrate all of this? And it has a lot to do with working with the university communities to think about how do we educate people, what are the software environments needed, how do we deal with all the data, and how do then we build applications on top of all of that. Okay, so that's a scary diagram to me. So what next? I think we have a really excellent high-level vision document and a lot of good structures that have been built by Dan here at NSF that I'm really building on top of now. We've started to address some of these things. Other parts of it we've barely touched. And so one of my messages is to you that the things out there that we've barely touched are my top priorities now to try to be building out. And they need to be integrated as much as possible, and they need to be coupled to the application space, or they won't be doing people any good. The applications are what drive everything. And so we need to have end-to-end integration. Now, all of this can be summarized in my view of what computational science really is. It is the science that's built on top of cyber infrastructure, which increasingly is all of science, I would say. Of course, theory and experiment are often aided by cyber infrastructure as well. So it's not just computing, but it's all of it, all balled together. And so if you read these National Academy reports and so on, they often talk about computational science as the third pillar of science and engineering. And in my definition, computational science is very broad. But I think we're not doing a good job of supporting it in a comprehensive way. And so the latter part of my talk coming up here is really focused on that. How do we support people who create, prototype, or use the next generation of cyber infrastructure? So what about campuses? I know I'm running a bit late here, so I'll just say I think we need to seriously rethink our campus environments and see how they can support these new modalities of research and collaboration, and what are the educational structures needed to support them. I'm sure you all agree very much. I'd like to figure out, with your help, what NSF can do to help catalyze the development of the right things on the campuses. One thing, this is a technical issue, but I think it would go a long way towards integrating campuses, and that's federated identity management. So that diagram on the right there is that infrastructure that people are trying to connect into. Every one of those bubbles and stars potentially has a different user ID, security policy, password, and so on. So it is literally just a nightmare trying to navigate that. And so there are new ways of dealing with this by having credentials on a campus level that are federated and then brought together through an organization, in this case a thing called InCommon. NSF has joined InCommon. If you don't know about it, I encourage you to take a look at it. If you've become a member of InCommon, I encourage you to really experiment with it, because NIH, in fact, has already adopted it. NSF is experimenting with it, and we're going to see how far we can get with it. But I wanted to just give you a brief idea. The dream of this is that you'd have a credential offered by your campus to all of your individuals. They would use that one credential to get into all the systems on campus and to all of the remote systems that are of interest to them. And so at NSF, the pilot program right now is to be able to get into Fastlane with a small number of universities. We're experimenting now to make sure this works. But as rapidly as we can, we want to expand this program. The TerraGrid is also experimenting with this and has a couple of stages of deployment that they're working on, so that if you were members of InCommon and your campus individuals have identities that are issued this way, they will be able to get into all of the TerraGrid facilities at some point in the future. That's where we're moving. So in terms of integration, that's an important aspect. It'll take a few years probably for us to really roll that out, but that's where we're going. Okay, let me come to the latter part of my talk then, which is about computational science activities. So the PITAC report, the Presidential Information Technology Advisory Committee from 2006, I think this was, has a very nice set of examples of computational science, and in the executive summary, they make some important statements that I wanted to highlight here. And I really live by these statements. I believe very strongly in them. Universities must significantly change their organizational structures if we are to remain competitive in global science. The next point I wanted to bring out was they say, together with theory and experiment, computational science now constitutes the third pillar of scientific inquiry. Now, I think we need to understand, what does that really mean, and are we supporting that appropriately? And I'll give you many examples in a minute where I think we're not. The next statement I pull out here is that itself a discipline, computational science serves to advance all of science. And at the moment, we have inadequate and outmoded structures in the federal government, Now that's me, so that's my problem, and it's also your problem to help me figure out what to do. And in the academy, so that means you on the campuses, we need to figure out how to better support this critical multidisciplinary field. So, to me, everything I've been talking about up to now is computational science, and we need to find a home for it. So, to me, this also means supporting the careers of people who prototype and develop the next generation of cyber infrastructure. So a lot of you are in information schools that probably have various levels of comfort and discomfort with different units on campus that you have to deal with, for example, computer science or mathematics or physics and so on. It's a new thing, information sciences and computational science, and very often the people that we really need to be supporting fall through the cracks, or they're at the fringes of their departments. And so I've seen this in many cases, and we need to find ways to support them. So one thing that I think we can be doing, aside from working with the universities to find a better process for supporting this new generation of people, is if the agencies could say in a more coherent way, we are supporting this, and for example, we offer career awards in computational sciences or some other area, that helps legitimize the fields. Often those are requirements for getting tenure and promotion for young assistant professors, and if we don't offer awards in those areas and yet we say it's very important, then we're not doing people a favor. So we need to rethink this in partnership with the universities, other directorates, and we're beginning to do this within NSF. I'm talking with the ADs on almost a daily basis about this particular issue, working with other agencies and with other countries. And I've personally made visits to groups in Europe, the European Commission, and also German groups, as well as some groups in Asia, on how we can better coordinate activities in these areas in computational science. So let me say just a few words to maybe provoke some questions in a few minutes here on my view on interdisciplinary computational science in academia. There have been many attempts to address this, and I've been through some of them myself. I've observed others. They almost all struggle. Some of them do very well. Some of them fail. And I think they're all very well motivated, but the trouble is it's a new thing, and it doesn't fit in traditional structures. So where does it fit in the curriculum, for example? A little bit of computer science, a little bit of math, a little bit of disciplinary activity, maybe computational science and engineering programs. Is that a department? Is it a school? Is it an information school? Many of you are involved in information schools. Should they be centers? Or one model doesn't fit all, of course. The different campuses will have different kinds of needs. Probably some combination of these things is needed. But what does it mean to support it? So I've personally observed vice chancellors and provosts talking very enthusiastically about interdisciplinary research, but not necessarily promoting, for example, joint mentoring committees for young faculty who are connected between different departments or different schools, and then their careers are sometimes jeopardized. Or are the incentives really there? We want to encourage interdisciplinary research. That means typically that people write papers together. Does that mean that they get the intellectual credit for those papers when they're up for promotion and tenure? What about funding? How much funding do they actually get credit for if they're on a 5 or more PI grant, or if they're merely a senior investigator but they're doing all the work in these large-scale collaborative grants? There are many overheads associated with these, and so those are many questions that I think we need to be really thinking through very deeply, or else we're going to be sputtering in the future as we try to get this field really rolling. How do we train and support people to work in this new and disruptive world? In some cases, I think we need some fundamental changes, and I'd like your help in figuring out what we can do at NSF to help support these things. So some specific examples that I have are within the Office of Cyber Infrastructure and across NSF, we will be trying to promote the development of a cyber infrastructure-based research agenda where we look at the sort of applied version of computer and information sciences where people would develop deployable cyber infrastructure, but of course there's a research agenda associated with that. It's not just developing, building some software based on some fundamental algorithms somebody developed. There are research agendas and what are the abstraction layers and all of that sort of thing as well. Career awards. You will see soon that we will be looking at rolling out career awards in cyber infrastructure development, information sciences, computational sciences that will explicitly call for people to be working in these areas. But we can go much beyond that. For example, issuing curriculum development grants that might help campuses really take this very seriously and rethink this. We might come up together with some best practices documents. Perhaps there's a forum we could bring together university provosts to have discussions like this. So the question I'm asking is, how can you help me figure out how we catalyze the creation of the 21st century university? So I just have a few slides left, and then we'll have questions here. So my rough plan for OCI in the future is to try to fill out all the holes in cyber infrastructure at the level that we can given our funding. So if you read, go back through my slides, the things I colored in red are where I think we have big holes. So those are the areas that I hope to be developing more funding in the future. Developing the workforce to take advantage of this, and then ultimately thinking of OCI potentially as a base for computational science, cyber infrastructure, and sort of the development and deployment version of information sciences. How do we do that? OCI will become increasingly active in building programs in these areas. So help me refine this plan. So in order to do this, we're rolling out some task forces. So over the next 12 to 18 months, we will be creating a series of task forces that will be led by our advisory committee on cyber infrastructure, involving all of the NSF directorates, not just from OCI, but all the directorates, membership from the community. That could involve as many of you as we can, and including having some workshops. These, over the next year to year and a half, will have some workshops, write some recommendations up, and then they will be given to us, and then we'll go back and we'll see what we can do about developing programs that will help support these ideas that we have, that we'll be getting from you. These are the task force areas that we've identified. One thing is we're looking at finding ways to reuse cyber infrastructure from one community to another. There are many cases where cyber infrastructure is developed by one group in biology, could be used by another, typically isn't. There are many reasons for that. We have to get past that. But there are even areas where, as I was illustrating in the beginning, in astrophysics we developed something that actually can be used in other areas, from coastal modeling to biology, computational biology, plasma physics, many other areas. So there's much that can be done to encourage the reuse of cyber infrastructure. But beyond that, we have 6 task forces that are to be done with the community. What are the software programs we need to develop on top of this complex investment in hardware that's been made and it will continue to be made? Campus bridging, how do we connect campuses to the national cyber infrastructure? Education and workforce development, what should we be doing to promote the next generation workforce to take advantage of all of this? The computing infrastructure, going beyond high performance computing, what is the roadmap there, involving distributed computing and high-end computing as well. Task Force 5 is data and visualization. As I said, that's probably the biggest challenge we have at a technical and algorithmic level, because it is so new and so rapidly growing, and we still have to learn what to do with that. The most important one that should be driving all of this is, what are the grand challenge science problems that really should be providing the motivation for everything we do, whether it's the education and workforce development or all of the cyber infrastructure rollout that's coming in the next few years ahead. So, translating this to future programs, I just wanted to close by reminding you of the big application areas that are so important. These are the areas, not just these, but all areas that should be driving the development of all the cyber infrastructure. So, 2 slides left, and then I know I've gone on quite a long time here, so I'll just say the critical lessons that I feel like I've learned are that, first of all, a very comprehensive approach to cyber infrastructure is needed to address the complex problems that we're looking at here. It's everything, and that comes back to that big picture that I drew. We need to develop that cyber infrastructure, and that is the background in which we should be solving the next generation complex problems. We have to educate people and generate the workforce that thinks about the collaborative and the technology issues for science and for society as we go forward. And cyber infrastructure really, I think, is now just at the beginning in terms of a platform, in a sense, for addressing these kinds of problems. So let me just summarize finally, and then we have questions. I think we have a great vision document in place, and I will encourage you to go back and look at that. We need a much more comprehensive and balanced cyber infrastructure than we've been able to build out so far. I'm working very hard on beginning to do that now and to getting the right kind of input so we'll do the right things in the future. I think the changes that are coming are very disruptive, and I want to partner with you to prepare. And one of the themes that we've been trying to promote here is that computational science and information science really needs a home, and we need a comprehensive approach both in academia and within the agency. So please help me as we go forward with the task forces. And I think I'll pause at this stage, and I hope there's some time for some questions now.